So now let's move on to how we implicitly derive an equation. If you take a look here at this example, x squared plus y squared is equal to 4. There's two ways to do this. There's an easy way and then there's a hard way. The hard way is our old way. So if we think about this as the old way, you might say, you know what, let's solve for y. Let's get that y alone. If we wind up trying to solve for y and subtracting x squared from both sides, we wind up with y squared is equal to 4 minus x squared. We still would need to solve for y by taking the square root of each side. If that's the case, you would wind up with y is equal to, yes, the square root of 4 minus x squared, but don't forget that there's a plus or minus on the inside. That means that we actually have two different derivatives happening at the same exact time. Why is that happening? Please note, guys, that this is actually the graph of a circle. So when you look at the derivative for this function here, okay, there are two different slopes of the tangent lines for the same value for x. One is going to be a positive version and one will be a negative version. That's why we're having those two different values. So let's say we were to continue and we broke this down to the positive version. So y equals to the square root of 4 minus x squared. And then we broke it down to the negative version of y equals to the negative square root of 4 minus x squared. If I go to take the derivative of the first one, we should write this in a little bit of a simpler form for ourselves, like y is equal to 4 minus x squared to the 1/2 power. If we go to find dy dx, in this case, we have 1/2 using our power from the exponent times 4 minus x squared to the negative 1/2 power. Just don't forget your chain rule to multiply by negative 2x, aka the derivative of your inside. If we start to clean this up, we do get that dy dx is equal to, we have negative 2 times 1/2, that is a negative number. We're going to keep our x with us on top. And notice here that you have a negative exponent or a negative 1/2. That means that we can move that term down and turn it back to a square root. That is one version of the derivative. Well, we can do exactly the same thing on the other side here. Rewrite this with a positive exponent, so 4 minus x squared to the 1/2. We can then solve for dy dx. That is negative 1/2 times 4 minus x squared to the negative 1/2. Again, chain rule for the inside there, times negative 2. And then we can clean that up. Dy dx is equal to negative 1/2 times negative 2 is a positive 1. We have our x left on top. And again, with that negative exponent there, we can move that term down and we can have 4 minus x squared to the 1/2 power. Note that that will make your derivative equal to dy dx is equal to a plus or a minus. Remember, we had that plus sign there. X over 4 minus x squared to the 1/2 power. There's got to be an easier way. This is so complicated. To solve for y was enough over the fact that we had to separate them, one positive, one negative. We had to take two different derivatives and then combine them back together to solve for dy dx. So how are you going to make this simpler? Well, let's take a different approach. Rather than forcing ourselves to solve for y, what if we left this equation in terms of x's and y's together? Don't solve for either of them. If that's the case, we can take the derivative of each term with respect to x right where it is. So let's start with the first term here. Let's just change that color so you guys can see it a little bit better. Let's start with this first term here, okay, x squared. If I take the derivative of x squared, that is going to be 2x. Now technically, remember, we're taking the derivative of x with respect to x, so technically there is a dx here, but remember dx is just 1, so we usually don't write it. So as we're taking derivatives of terms with x's, we usually just take their derivative normally. We don't have to worry about writing that dx. So the derivative of x squared here is just 2x. Let's move on to the next term, however, and let's focus on that y squared. Now we have to take the derivative of y squared. Taking the derivative of that term is going to look something like 2y, just like the 2x, except for the fact that y is a function of x. So when we apply our chain rule here, we must multiply by dy dx. Again, taking the derivative of y with respect to x. Anytime you have a term with a y, you should see dy dx when you're taking the derivative of that term. You can then finally move on to the last term here, which is your 4, and the derivative of that 4, which is a constant, is just 0. Last but not least here, gentlemen, you must actually solve for dy dx. Get dy dx by itself. So we're going to subtract 2x from both sides. We have 2y dy dx is equal to negative 2x. And you can divide both sides by 2y. Divide both sides by 2y. That means that dy dx is equal to, notice the negative 2 over 2 reduces to a negative 1. So that is going to be x over y with a negative number in front. So you might be saying to yourself, hey, why do we have two different variables here? Why do we have two different derivatives? Well, there's got to be a way for us to prove that these derivatives are actually the same. If I take a look at this derivative, and I take a look at this derivative simultaneously, side by side, how do we see that they're the same? Just written a little bit differently. Well, if we take a look here, notice that we have the x on top, right? So that seems to match. If you take a look at the bottom here on the right-hand side, notice that you have a y. If you look at how we solved for y on the first side, we have y is equal to plus or minus the square root of 4 minus x squared. Well, guess what? You have a plus or minus. Remember, it doesn't matter where your signs go. And here is your 4 minus x squared to the 1/2 power. That's your square root of 4 minus x squared. So these are exactly the same, but if you take a look at the orange side, that's a whole lot simpler than having to solve for it in the other direction. So what we're going to be following for the next week or so is implicit differentiation. And implicit differentiation says you have an equation in terms of x's and y's. It's going to be really hard to solve for that y. So we're going to take the derivative as it is, and we're just going to apply our chain rule as we go. Remember that terms with x's, you're going to take the derivative of it normally. However, terms with y's, you're going to have to use your chain rule and multiply that by dy dx. After that, you will have to solve for dy dx and isolate it alone. Note here that since your equation was given to you in terms of x's and y's, that your derivative is also coming to you in terms of x's and y's. That is okay. That is supposed to happen. Your derivative should come to you in terms of x's and y's, given that nothing simplifies. When we're looking for implicit differentiation, guys, something to really remember is an abbreviation like diffs, right? We're going to differentiate both sides with respect to x. Once we do that, we're going to isolate the y prime, get all your terms with y prime or dy dx, right? This is another word of just saying dy dx to one side. You're going to factor out your y prime or factor out your dy dx, and then you're going to solve for y prime. Just be careful, okay? Because you might have to substitute y back from the function to the answer. Not always, though. You can leave it in terms of the two variables. So take a look here, okay? Here's a couple of examples. For example 1, okay, it's asking to solve for dy dx. Notice we'll start with the first term. Our first term only has an x in it. That's great. That first term's derivative is just going to be 3x squared using our power rule. The problem is, however, on your next term, note we have two variables, x's and y's together. When you have x's and y's together, this is actually a product. Here, we're going to have to apply our product rule. we are multiplying 3x squared and y. A lot of the times, gentlemen, it's very easy to isolate the y and make the y a term on its own. So let's use our product rule here. We have the first times the derivative of the second. The derivative of y is dy dx, plus the second, which is y, times the derivative of the first, which is 6x. That takes care of that term there. Now we can move on to the next term and say, all right, let's take the derivative of y cubed. That just looks like a power rule to me. So we have 3y squared, but don't forget, this term has a y in it. So we're going to have to use our chain rule on that y and multiply it by dy dx. Once we finish that term right there with that dy dx chain rule, we can finally move on to the constant. And the derivative of that constant will be 0. Notice here we have two terms that have a dy dx. You have that term here, and you have that term here. We're going to move the terms with the dy dx to one side. So that means that we have 3x squared dy dx plus 3y squared dy dx. And we're going to move the other terms to the other side. Minus 3x squared minus 6xy. I just wrote the terms there using commutative property. So we have minus 3x squared minus 6xy. Notice both of these terms have a dy dx, so we're going to factor that term out. So here we will have dy dx. That will be equal to, not equal to yet. We'll have 3x squared plus 3y squared, what's left over when it's factored out, equals to negative 3x squared minus 6xy. And then we're going to divide both sides to still isolate dy dx. We have to get that alone here. So I'm going to divide this side by 3x squared plus 3y squared. And I will do the same to the other side. Divide that by 3x squared plus 3y squared. Notice that these cancel. And your derivative, or your dy dx, is just going to be equal to negative 3x squared minus 6xy over 3x squared plus 3y squared. That is your derivative. That's a lot simpler than taking that equation and having to solve for x or having to solve for y, and then take the derivative from there. So again, I know that this is new, okay? But again, you have an equation with x's and y's together. We're using our chain rule to take the derivative of each term as it is. And then we're going to have our derivative in terms of x's and y's. Notice for the next question, they're asking is the relation increasing or decreasing at a specific point. Notice that point gives you an x value and a y value. You can actually justify to yourself that this point lies on your equation. We have x to the third plus 3x squared y plus y to the third is equal to 1. If we plug in x values of 1 and y values of 0, we can justify that 1 to the third plus 3 times 1 squared times 0 plus 0 to the third will equal to 1. Here 1 will equal to 1. That means that that point does lie in that equation. So just justifying that this is a point on the graph. If you want to know if the relation is increasing or decreasing, remember that this means that you're going to be looking for your derivative to be positive or for your derivative to be negative. Now, that was terrible notation. I shouldn't have written f here. We should have written dy dx because that is our derivative in this case, or dy dx. So all we got to do is take our derivative, dy dx, and we're going to have to find the derivative at that point. Notice our derivative was already found for us, right? So we're just going to move that down, okay? And all we need to do is put in the value for x and the value for y. That's negative 3 times 1 squared plus 6 times 1 times 0 all over 3 times 1 squared plus 3 times 0 squared. if we clean that up, we do get a negative 3 over 3, which is a negative 1. That means that since our derivative is negative, or since dy dx is less than 0, that means that your function is actually going to be decreasing. Right? So just plugging in your x and your y. Then we can move on to using implicit differentiation to write the equation of a tangent line or a normal line at that point. Remember, if we're using the equation for a tangent line, we can use y minus y1 is equal to m times x minus x1. You can use your point slope form, okay? Remember, if we know that the derivative at a point is equal to negative 1, that's also the slope of your tangent line. So we have a point here, we have an x1 and we have a y1 and we have a slope. So we're really ready to plug everything into this equation for your tangent line. For the tangent line here, we will just have y minus 0 is equal to negative 1 times x minus 1. You could clean that up and just make this y equals 2 on the left-hand side, and you can make that into negative x plus 1. That will be the equation for a tangent line. Recall, though, for normal lines, that the slope is the negative reciprocal because normal lines are perpendicular. So the slope for the normal line, that is going to be the negative reciprocal, or positive 1. Remember, if you have negative 1 over 1, its negative reciprocal is going to be a positive 1 over 1. So again, same point, still passing through the same point, y minus 0, except at this point, your slope is now the negative reciprocal, or positive 1. You can clean that up and just write that in the form of y equals to x minus 1. We have one last and final question here to go through before you are going to complete the rest of the work by yourself, and that is just example number 2. Example number 2 says for each given equation, or the one given equation, find the second derivative. Find d squared y dx squared in simplified form. That means that you're going to have to find the first derivative and then find the derivative of that as well. So again, let's go through this implicitly. We look at the first term and we see here that there's only one term. So there's only one variable in that term. So if I take the derivative of that, that will just be 18x. When I move on to the next term here with y squared, that's going to be plus 2y. Don't forget your chain rule, dy dx. Last but not least, we can move on to the last term, and the derivative of 15 is a constant, so that will give you to 0. So if we clean this up and solve for dy dx, we have that 2y dy dx is equal to negative 18x. You can divide both sides by 2y, and that means that dy dx is equal to negative 9x over y. Well, we got to take another derivative, one more to get that second derivative. So here's the thing. As we're looking here at the first derivative, notice that the derivative here is a quotient. That means when we go to find the second derivative which also says d squared y dx squared, okay, all we got to use is our quotient rule. We have the low, or the bottom function, times the derivative of the top function. The derivative of negative 9x is negative 9, minus high, that's negative 9x, all right, the top function, times the derivative of the bottom, or d low, that is dy dx, all over low squared, or the bottom squared. That's going to be y squared for us. Now, if you take a look here, again, derivatives can be written in terms of x's and y's, but we just can't have derivatives inside of the derivatives. So if you take a look here, this term here with dy dx, we just need to replace that with this right there. We already solved for dy dx in terms of x's and y's. So we just need to make a quick little substitution and do some cleanup. So that means that we have d squared y dx squared, aka the second derivative. That's going to be a negative 9y. This will be a plus 9x, and we're going to multiply that by a negative 9x over y. And that also will be over y squared. We just need to continue cleaning this up. So moving over to the right, let's write this as negative 9y. Writing this as a single fraction, this will be minus 81x squared over y. And that will be over y squared. The only thing we really need to do here, gentlemen, is to take this ugly fraction, because we got fractions within fractions, and just write it as one fraction. Note, you can turn all terms into a fraction, and you can multiply it by your LCD. The LCD for this entire fraction here would happen to be y. Notice that's going to be your common denominator. So every single term here is just going to get multiplied by y. That means that our second derivative, when we clean it up, we have our first term here, okay? That's going to be negative 9y squared. Notice nothing cancels. And the second one, notice that the y cancels with the y. So we're left with minus 81x squared. In your denominator here, though, again, nothing cancels. So you're just going to be left with y to the third. Now that your derivative is written in terms of x's and y's, you're good to go. We've taken two derivatives, the first derivative dy dx, the second derivative d squared y dx squared, and the second derivative is written in terms of x's and y's. As you move forward in the homework for this evening, you will just be reproducing the things that you saw above. Please feel free to reach out to the discussion board with questions, and also feel free to email any questions that you have to myself or to Dr. Summers. Good luck, gentlemen, and enjoy implicit differentiation.